So now we're going to take a look at how to compute limits for functions in practice using the rulebook. Now, what's the rulebook? So the rulebook, I mean, you can go to basically any book in calculus, and it says, for instance, so if f of x tends towards L, g of x tends towards m, as x tends to A, then, well, the sum f of x plus g of x tends to the sum of L plus m. If I do minus here, I get minus. If I do the product here, I get the product here. And if I do division here, I get division here. Of course, then I have to be careful that m is not 0 and that g stays away from 0 at least as x approaches a. And you have this rule of composition. So this thing here, the easiest way to write is basically that if f is continuous, then you get this. So here if f continuous, you also have to be a little bit careful of that things are well defined here. And then you have the squeeze theorem, and that's more or less it, okay? And as I said, you can basically go to any textbook in calculus or online or whatever, and you'll get these written out in a nice way. So now the point here is to talk a little bit about how we apply them in practice. We already in previous films talked about corresponding situations or analog situations for sequences. So I'm just now going to add a little bit about what is new when we look at limits of functions. So as an example, we can let x tend to 1 when we look at this quotient here. And of course, when we look at sequences, we only dealt with x going to, basically x going to infinity, right? Now we're having x going to a finite point. Something that's tempting here is just, why not just replace x by 1 here and x by 1 here? So I mean, clearly, if I take the limit as x goes to 1 in this expression, well, it should get closer to whatever value it has at 1. Similarly here. But if I do so, I see that I get a 0 divided by 0 here. Of course, this reflects the fact that if I call this f of x, I'm here taking the limit towards a point where f of x is not defined, which is a typical situation when we want to consider limits. The limit is basically a tool for checking what a function does close to points where it's not defined, close to infinity, close to minus infinity, or in this case, close to 1. Now, in writing 0 divided by 0, I'm basically saying that I cannot use these rules because this division rule only applied if m is non-zero. So what can I do? Well, then we need to rewrite this expression. And of course, this should be fairly okay. So I can write this out using or I can expand this using the conjugate rule. So I'm getting x minus 1, x plus 1, x minus 1 here. I scratch those two. I get here lim x tends to 1, and then I get x plus 1 here. Now I have an expression where it's clear that when x tends to 1, this tends to 1 plus 1 equals to 2. This is basically a new rule of thumb. So if you here have an expression where when you replace x by its limit, you get something that makes sense, so not 0 by 0, but for instance 2, then go for it. So this is basically the algebraic finger playing along, because what we see now is that this f of x here, well, it's nothing but this graph here, except that the value 1 is not in its definition. But what is its limit? Well, if I let my finger follow the graph as x tends toward 1, I will tend toward this height here, and this height here is at 2. So intuitively, in terms of the visuals here, it's clear that my limit should be 2. The algebraic version of this rule of thumb, it's that if you can get away with just replacing x by its limit, if you get an expression that makes sense, then go for it.